B.Tech student can do, then why computer science students cannot? Actually, this topological motion planning is one of the concept which is used in robotic solution. So you are interested in robotics, isn't it? So you are not interested, huh? You are not interested. Here, so this is a simple, that is an example. That is here we have to do this object, okay? Only horizontal and vertical movement is possible. So what you have to do? So this object has to reach this destination. Okay, that is the thing. So here, this is the first movement. Then we have to go to the same pattern. We have to go to this third movement, and then we have to rotate to get this fourth movement, and then 5, 6, and 7. So here we are using translation as well as rotation. Translation means suppose I am here, I am moving like this. This is translation. Okay. So instead of that, if my position is changed from here to here, then it is somewhat. Okay. So translation as well as rotation is used here. So the only thing is the movement should be collision free. That is collision free in the sense we should not collide any blocks or any. Suppose there is some hurdles in the. Suppose in the room there is so many chairs. I want to move from this position to that position without intersecting or without touching the chairs. So that is the main. Okay. So collision free trajectories, and robot should reach the goal location as fast as possible. So we should not move slowly. So we have to get to the continuous path so that we can reach the destination quickly. Okay. Next. And here already I have discussed what is a configuration space. So configuration space is nothing but that is what we have taken into the consideration. So here the question of the objects are denoted by configuration, and here it is denoted by Q. Next. And this is the example that already I said. This is 2 dimension. We have only horizontal as well as vertical movement. And here we have 3 dimension. That is horizontal, vertical, and rotation. So that is translation as well as rotation. Okay, next. And here, so the space means configuration space. We are considering all possible configurations. That is all possible positions is taken as configuration. So all possible positions are considered as the configuration space. Okay. And the topology of the spaces. That is, if you consider real line, we know. If plane, we know plane is nothing but R2, isn't it? And that is 2-dimensional plane means it is R2. And 3-dimensional space means it is R3. So we can have our Euclidean metric or Euclidean topology there. So that is nothing but the R2 means it is a Cartesian plane, R3 Cartesian space, isn't it? So likewise, here the configuration space need not be a Cartesian plane or Cartesian space. Okay, so it need not be our visual space. Okay, and then the space that is the configuration space is nothing but a topological manifold. It is some advanced one. That is, should be a compact Hausdorff space, and the open walls are homomorphic to some consider the arm of a robot, and each position here you just see that this position is taken as one cue point. Next position it is extended from some extension. So here it is translation, and this position is rotation. Okay, and the next it is this position is stand here, so that is the rotation, and this position is move to this position, therefore it is translation. So here the movements the positions are involved with translation as well as rotation. Each position is denoted by configuration. So collection of all these positions is denoted by configuration space. Okay. And here, so in general, suppose if you consider this room as your space and the chairs as our obstacles. So these are the obstacles. Okay, so obstacles means our aim is we have to move the robo from one position to the other position without touching the obstacles. Okay, we cannot cross the obstacles, that is we cannot touch the chair. Okay, but we have to move from one place to the other place. Okay, so here what is the freeze? This W is nothing but our configuration space, that is the Intellige space. So Intellige space is our W, or it can be treated as a subset of R power M, or it can be taken as that is configuration in the configuration space. Okay, so this is the configuration space, and this QI is the initial point and QG is the goal point. So we have to move our robo from this QI to QG. Okay, that is initial position to the goal position. We have to move our robo. Okay, in such a way that we should not touch this obstacles. Okay, so what is the configuration space? Here, the entire thing is configuration space. So configuration space may contains the obstacles also. Okay, so what is free? So free space in the sense we are omitting the obstacles remaining space. Okay, this white spaces are called the free space. White spaces, that is the spaces which are shaded in white, they are called the free space. So we are removing, that is A of U is nothing but the configurations removing, that is A of U is nothing but the configurations of the robo. So where the robo can move, we can move the robo of the robo. So where the robo can move, we can move the robo from here only. Okay, so our aim is we should not touch we should not cross the obstacle, isn't it? So we should not cross the obstacle. Therefore, this A of Q is the QI's position. Okay, that is configurations. A of Q is configurations, the collection of all configurations. Intersection, this O is obstacle. Okay, it should be empty. That is, the robo should not meet the obstacle. Okay, therefore we can move from in between these white spaces alone. This white space is called space, and obstacle is nothing but the complement of the spaces, obstacle space. Next. And the same thing here, we are considering, that is in actually motion planning, we can consider the robo as a point. If we consider robo as a point, so these are obstacle, the black shades are here in the obstacle. So we can, the robo can touch the edges of the vertices of the obstacle. Okay. So, but when we consider, you may hear that the robo is cleaning the floor. There is a mop, it's automatic. You may see in Amazon, etc. Isn't it? So that is actually a robo. Okay. So we are using to cleaning our surfaces also. That is so cleaning robos. That is also considered. That is look like a circle. So suppose instead of a point, consider the object or the robo as object of the robot. That is the position. Okay, that is the symmetric sign. Because circle is a symmetric one, isn't it? Yes, circle is a symmetric object. So in that case, suppose the robot is denoted by either a point or a symmetric object. So in that case, that is proclaiming robot is a symmetric object because it can be treated as a circle. Okay, likewise. So in that case, what you have to do is, so outside the obstacle, you have to choose the boundary of the boundary of the our robo, okay, and then you have to fit that portion also. That is, we should not that is, the robo should not come nearer to this portion. That is, if this is the robo, that is symmetric object. In that case, robo, if you draw this, isn't it? This is the, if it touches if the robo touches this blocks of the obstacle, it will be like this, isn't it? So we have to remove from the center to the radius distance. Okay, we have to remove the radius distance from the obstacle. So that also considered as the obstacle. So if it is point, no need to bother about that. As a symmetric object, you have to make some radius. That is, radius means the radius of the symmetric robo, isn't it? So that radius has to be removed from the free space. Okay, that also considered as the obstacle. So based on that obstacle, we have to consider the path. Next. And what is the problem definition? So what is the motion planning? Here we have a configuration space, and a free space is a subset of configuration space, isn't it? So configuration space is union of free space as well as obstacles. Okay, and we are given initial point as well as goal point in the free space. We have two positions of robo. That is, we have to start from this, we have to end from this, and we can move only in the free space. So we have given 2 points in the free space, and the problem is, this is the topology now. So we have to find a continuous path from closed interval 0, 1 to the free space. This C free means free space. Consider a path connecting this QI and Q. You have to consider a path connecting QI and QC in free space. That is continuous path in the sense any break. You can draw a line without any disconnect. Okay, so that is our next. So here, what is the continuous path means? So in the previous example, we have this initial point and the goal point. So we can draw a continuous path like this, or you can have a continuous path from this one to this one, or we can have continuous path. But our aim is, again, we have to get a here. Okay, next. So there are so many, that is discretization in the sense the continuous terrains. That is, we have the configuration space that can be divided into so many that is spaces. Okay, so that is, for that we have basic methods. So one is combinatorial planning, another one is sampling based planning. So combinatorial planning is drastically used nowadays. Okay, and sampling based planning is also used for high dimensional configuration spaces. Suppose our dimension of the configuration space is very high. In that sense, we are using sampling based. But for the simple 2-dimensional or 3-dimensional or some finite dimensional spaces, we can use this combinatorial planning. So under combinatorial planning, we have this roadmaps method, cell decomposition, and potential feedback. Okay. These three are again coming under combinatorial planning technique. So what is the roadmap? So usual sense road. That is, roadmap means usually if you have any city, you can connect to the places of the city by road, isn't it? So that same procedure is used here. Under one is by means of drawing the visibility graph, we can attain the continuous path. So our aim is You have to find a path that is a continuous path with the minimum cost from initial point to the goal point. Isn't it? So, you can find the continuous mapping using